thanks very much for the invitation. It's a real pleasure to be here, and I'd like to talk about deep neural networks and some of the fears around them, and in particular, diving right in, I'd like to focus on some of the methods that are being proposed for dealing with fears about AI, particularly from a regulatory perspective. I've been involved in a bit of a movement that is called digital humanism, that is really about this effort to ensure that technology develops in ways that are beneficial to humans. And as a consequence, I end up talking to quite a few policy people, and I feel like one of my roles in this is to try to help them understand what's really going on with the technology. So the idea behind algorithmic transparency is that if you know what the operations are that are going on in the making of a decision, for example, the use of an AI in granting or denying a loan, then you can better defend the decisions that are being made. And some of the regulatory proposals, in fact, in Europe, the GDPR actually includes a clause that gives a right to an explanation, although legal scholars seem to think that it's unenforceable in the GDPR, but there's various movements underway to get more enforceable laws. But one of the problems is that understanding the operations in the computer don't really provide what anyone would call an explanation. And I suspect that everyone in the audience here is quite familiar with the way deep neural networks work, so I won't linger on this too much, but pictures like this are pretty common. They're grossly oversimplifying the problem, of course, because the inputs to a deep neural network are not just 4 numbers, as might be implied by this picture, but they're a list of millions of numbers, and each of the connections in this picture are really very simple arithmetic operations. They're just multiplying those numbers by a weight, summing them, applying some nonlinear function to get a new list of numbers, and doing this in a multiplicity of layers. The training operation, which calculates the millions or sometimes billions of parameters in these numbers, is pretty simple as well. In fact, back when I was working at Bell Labs in the early 1980s, I was doing what is now known to everyone as backpropagation. It was really adaptive equalization at the time, but it was essentially the same algorithm, a pretty simple algorithm, but it's a large algorithm, a lot of data. There's a recent study from UMass Amherst that estimates that training one natural language processing engine consumes more than 600,000 pounds of carbon dioxide, or emits more than 600,000 pounds of carbon dioxide, which is roughly equivalent to a fully loaded passenger airplane crossing the Atlantic Ocean. So the algorithms are simple, but the data is large, the number of operations is enormous. And so if you explain to a person in terms of these operations why their loan was denied, is that going to be a useful explanation? Well, I think the answer is obviously not. So what actually do we mean by an explanation? So what we want from an explanation is you start with the input data, what was fed into the algorithm. You give a sequence of logical deductions where each deduction conforms with some rules of logic, and the sequence terminates with a conclusion. But if you give an explanation in terms of billions or trillions of arithmetic operations, that's just not going to be a useful explanation to humans. So what is a useful explanation for a human? Well, it's really just what I just described, and I can borrow from Herb Simon. Herb Simon may be the I think, is the only person who has won both a Turing Award and a Nobel Prize. He got the Nobel Prize in economics for this thesis of bounded rationality, which suggested that humans are actually not very good at the step-by-step reasoning using clearly explicable rules of logic. The problem is that the human brain, when presented with the need to do such reasoning, can handle a few steps, certainly nowhere near billions. You know, maybe a really smart person can handle a few dozen steps, but it's a far cry from the number of steps that would be required to be able to interpret these algorithms as giving any kind of an explanation for the decision. So how can we find an explanation? Well, actually, humans are very good at synthesizing explanations in a post hoc way. So I will borrow an example this is basically 2 levels of indirection, because I learned about this example from Daniel Kahneman's book, and he was taking the example from another study. The authors are shown on the bottom of the slide, but this was a study of Israeli judges who were hearing parole cases. And the study found that there was a very high correlation between denying parole and the time since the last food break. I suspect, however, that if you asked any of these judges to explain their decision about the parole break, they would have no trouble coming up with a rational explanation for their decision. They would give you the factors that went into the decision, and those factors would not include anything about the time since the last food break. So I'd like to make a provocative prediction here, which is that as soon as we have enforceable laws that demand an explanation for the decision made by an AI, then researchers will train an AI to provide a convincing explanation for any decision. And in fact, I can give you some sense of how to design such an explanation machine. We can use this technique called generative adversarial networks, where we pit 2 DNNs against one another. So the first neural network, we train it so that given the case data and a decision, it synthesizes an explanation. So it's going to give us a sequence of logical deductions that has to be short. Okay. Machine 2, we train it so that given a decision and an explanation, it decides whether the explanation was generated by a machine or by a human. There's a lot of case data that we can use, in fact, to obtain explanations for decisions generated by humans, in certain domains, at least in legal domains, for example. These are readily available. So all we have to do then is pit these 2 machines against one another, and we effectively get a machine that is trained to give us explanations for any decision. And I think that that's obviously not what people would hope was the outcome, and it's certainly not the intent of regulations that provide humans with a right for an explanation. So how do actually humans make decisions, right? Do humans make decisions through short sequences of rational deductions? Well, sometimes, but actually more often not, and quite rarely is that the only mechanism involved in making decisions. So again, quoting from Daniel Kahneman, who is another Nobel Prize winner. Daniel Kahneman is a psychiatrist and a psychologist, sorry. And he, in this book, Thinking Fast and Slow, where he presents his theory in a very accessible way, he divides human thinking into 2 subsystems, which he calls System 1 and System 2. And System 1 is the quick, intuitive, inexplicable decision-making, what most of us would call intuition. This is where, presented with some scenario, you kind of immediately have a gut reaction and you think you know what the decision is going to be. And System 2 is the rational decision-making, as in the Herb Simon sense, the sequence of logical deductions. And his observation is that actually rarely is System 2 the only mechanism involved. I mean, I say rarely because, you know, sometimes it is when we're constructing mathematical proofs, for example, where there is some role for system one in kind of guiding our thinking, but ultimately we're trying to come up with a system two kind of explanation. But my claim here is that only when system two dominates does the true origin of a decision correspond to anything we would accept as a rational explanation, an explanation that would be suitable for humans. So for system one, really the only accurate explanation we have for a decision is that millions of neurons fire. And that's not going to be a very satisfactory decision. Imagine if you asked the parole judge why he denied parole for this particular candidate, and he starts to explain the firing of the neurons that led to that decision. It's just not going to be a satisfactory explanation. So my claim is that deep neural networks are much more like system one than they are like system two. And people, when I talk to people who are not technologists, they're very surprised by this claim. They think that there's this preconception that a computer is doing deductive logical reasoning. That's what computers do, right? Every step of the computer is rational in the sense of Kahneman. And they presume that from that observation about how computers work, that a programmer, which is the person responsible for telling the machine what to do, surely can give you an explanation for any outcome from the computer program. And they're very surprised when I tell them that that's actually not the case, that if you ask the programmer why a particular DNN yields a particular decision, it's really quite difficult for a programmer to come up with anything like an acceptable rational explanation for that decision. So, but rational decision making, I mean, it's fundamentally algorithmic. What is an algorithm? Well, an algorithm is where you start with input data, follow a sequence of steps, and each step follows well-defined rules, and the sequence terminates with a conclusion. That's an explanation, right? But the problem is the scale of these things, right? If you further limit the data to a discrete set, then algorithms are equivalent to Turing machines here. And, you know, Turing machines are supposed by many to be the sort of best model that we have for what computers do. And so it seems that they're really doing this kind of algorithmic decision making. So if you put this notion of an explanation next to the notion of an algorithm, they look identical. But the difference here really is a matter of scale. An explanation is a short algorithm. And the well-defined rules of logic have to be socially agreed upon in this case, which of course adds some complexity to coming up with explanations. So is system one in the human brain algorithmic? Okay. According to Simon and Kahneman, system one decisions are not rational processes. They're not usefully described in this way. One very nice analogy that is due to the philosopher John Searle is, you know, I mean, ultimately, of course, a system one decision made by a human is the consequence of the rules of physics, the laws of physics, right? I mean, the neurons behave according to the laws of physics, and so you should be able to explain the processes that yield a decision, a system one style decision. But the John Searle's analogy was, well, okay, that's a little bit like, I'll update his analogy a little bit. It's a little bit like trying to explain the emergence of the Ukraine war in terms of electron-proton interactions. You know, ultimately, it is the consequence of electron-proton interactions and other basic rules of physics, but you're not going to get a useful explanation for the emergence of the Ukraine war that way. It's an interesting sort of fundamental question whether ultimately system one decisions are algorithmic. There's been a lot of effort in neuroscience to try to interpret cognitive functions in an ultimately algorithmic way. One of the people who initially proposed that this could be done was Jeff Lichtman of Harvard, and he set out to understand the connection structure in brains and to figure out whether you could in fact explain the operation of brains in terms of these the structure of the connections. In fact, he coined the term connectomics for this idea that that maybe if you could understand the architecture at a detailed level, you could in fact be able to come up with reasonable explanations for how the function works. And he set out to actually understand the connection structure. And the picture that's shown here is from a very tiny section of mouse brain that he used a very clever technique of making very thin slices of pieces of the brain, scanning them, and then using a computer to reconstruct the three-dimensional structure. His conclusion from this study is that the connection structure is wildly random, and that understanding its structure will yield essentially no insight into the operation of the brain. It was, in some sense, a very beautiful negative result. It's not that surprising. I mean, there's a lot of machines, even man-made machines, that are really actually not usefully modeled by algorithms. You know, a machine like this, a mechanical machine, we might describe using differential equations, for example, which might give us a very declarative description, but differential equations are not actually an algorithmic description of anything. In fact, particularly nonlinear differential equations that have chaotic behavior cannot be replicated by algorithms. Their behavior cannot be reproduced algorithmically. So it shouldn't be that surprising that there might be processes in nature that are not actually ultimately describable using algorithmic techniques. It turns out that even deep neural networks may not be fundamentally algorithmic. So there's this sort of, I don't know, a little bit of a sort of cult branch of the DNN research world called Reservoir Computing that takes big chunks of the central parts, the intermediate layers of a neural network, and replaces them effectively with some blob of physics. So a wide variety of different blobs of physics have been used, right? Carbon nanotubes, buckets of water. This is where the term reservoir computing comes from. It's from some early experiments with just buckets of water. People have used in vitro cell cultures. So you replace large chunks of the center of the neural network, and you find that you really only need to train the outer layers, and you can get very effective trainable neural networks. So Tanaka, who's one of the researchers in this, one of the lead researchers in this area, one of the proponents, has made a provocative conjecture that it's possible that some brain regions actually work as reservoirs. They're essentially random blobs of physics that give you a very rich set of nonlinear functions, and they don't participate in a large way in the training operations. They just provide you with this this reservoir of a rich set of nonlinear functions. The neuroscience support for this is pretty weak at this point, but it's a provocative conjecture, and the fact that that people have been able to come up with effective neural networks that are capable of competing with the algorithmic versions sort of suggests that the fundamental operations may not actually be necessarily algorithmic, and that the implementations that we have of neural networks today may be essentially brute force computer simulations of fundamentally non-algorithmic operations. So there's other kinds of things that people keep proposing about, you know, how we might go about ameliorating the fears that people have about AI, right? One of the ultimate goals that people have is artificial general intelligence, and I think the hope here, which is actually also a rather scary proposition, is that we'll create machines that are more human-like and that we can interact with them in human-like ways. And since we're fairly experienced with that, maybe that'll be better. I think that we've actually demonstrated that we're perfectly capable already of creating human-like behaviors out of AI. So one of my favorite examples is this chatbot that Microsoft released in 2016 called Tay, which was designed to interact with users on social media in a human-like way. And it was particularly, their hope was that it would develop, the vernacular language of hip youngsters who are using the media. And unfortunately, it very quickly did that and did it extremely well. It quickly learned to write vulgar and racist tweets, behaving in a way that actually, sadly, is very reminiscent of the way many humans interact with such media. So that's not a particularly appealing strategy, I think. There's another kind of silver bullet. People say, well, all right, let's keep humans in the loop in any decision. So, the AIs can give recommendations, but let's make sure that humans are the ultimate decision maker. Unfortunately, we've already learned the hard way that humans are easily manipulated by the machines. And so keeping them in the loop doesn't necessarily mean that you automatically get good decisions. There's a couple of very good articles in this book that I was a participant in editing. This is an open access book that you can download that has a collection of 44 essays on various perspectives from a wide variety of disciplines on this problem of digital humanism. And it's already been downloaded. I checked a couple of days ago, and it's been downloaded more than 230,000 times. That doesn't mean that all those people have read it, but it does suggest that there is significant interest in the topic. But two of the articles that I like a lot focus particularly on this issue that machines, in fact, effectively manipulate humans. So let's take a look at how this works, right? The reality of the internet today is that we have access to far more information than any individual human can possibly absorb. This has not always been true for humans. In fact, when I was starting out my career as a researcher, it was quite laborious to seek out information. I would have to go down to the library on the first floor of the Homedale building at Bell Labs and dig through, Bell Labs technical reports dating way back to find information. Today, you just Google for stuff and it shows up right in front of you. And the fact is that the information that's available to us vastly exceeds what we can possibly absorb. And my claim is that this makes the use of AIs to filter information both necessary and inevitable. We really can't, there's no other way to manage this information flood. The other side of the coin is that there's an information economy that leads the AIs to filter, and to filter in a particular way that manipulates the humans. So human decision-making, I claim, is actually no longer independent of the machines. So this point was made very forcefully by my colleague, Stuart Russell, who is an AI researcher, famous for his work in reinforcement learning. But he points out in this book, this recent book that he published called Human Compatible, that predictable humans can be reliably presented with advertisements that they will click on. And then he points out that political extremists are more predictable than moderates, and that there's a feedback loop, that the machines, because of the functions, the optimization functions that they're equipped with to do the training, they will naturally feed people information that will tend to make them more politically extreme, because this makes them more predictable, and the machines can therefore get better responses when presenting advertisements to the individuals. So in a recent book that I published called The Coevolution, I coined the term for this an information apocalypse. And the term apocalypse is very carefully chosen here because if you go back to the original Greek meaning of the word apocalypse, it means an uncovering, a revealing of information. And the observation here is that because of the vast quantity of information that we're dealing with, this information economy runs a risk of creating islands of disjoint truths. Now, I want to emphasize the word truths here because many people focus on the fake news, the false information, the deep fakes part of the problem. And I don't want to discount those problems. I think that it's a very serious problem that there's a lot of simply false information available on the internet. But my claim is that even if you do the thought experiment and assume that all of the information on the internet is true, you still run a risk of getting groups of people who don't share any truths. They're living in these islands of disjoint truths, and that is not necessarily a much better situation than having people who are sharing disjoint lies. It's not necessarily much better. So really, let's ask the question. You know, are we in control? That's a common question. Well, what do we mean by we, right? Humanity, all 8 billion? Well, you know, can 8 billion people control anything? I don't think so. So let's not even go there. That's not the question, right? So then, okay, so who is the we? Is it the engineers, the programmers, the CEOs, the users? Are any of these people actually in control? Well, what do we mean by control? Well, one sort of naive answer is we could pull the plug, right? We could turn off all the AIs, right? Well, think about it. What would happen? What would happen today if we had to shut down all the computers on the planet? Now, the presumption here, now some of the computers don't have any AI in them, but a lot of them do. Think about what would happen, for example, if we had to shut down all of our credit card network, which depends very heavily on AIs for fraud detection. This, you know, we reached, by the way, according to estimates, just a few days ago, the planet reached a population of 8 billion. Possible to feed 8 billion people on the planet without the technology that we're using? I'm not sure. So we may already be in a situation where we're well beyond the ability to simply pull the plug on these systems. So I don't think that's going to be a useful notion of control. So I think the only useful notion of control that I can come up with this question, are we in control, is, well, are we in control of the trajectory, the design of the systems? How, you know, we design them, we choose to use them. Surely whatever we is in this case, the engineers, I guess, are the ones who decide the trajectory of the system. So to clarify the question, do engineers, programmers, business leaders, or users determine the outcome of technology development? My claim is not so much. This is the major theme of this book that I published 2 years ago called The Coevolution. And this is a picture of me standing in front of a ship that was built by King Gustav II Adolf some 350 years ago or so in Sweden. And this ship, when it was first launched, it took a party of some 200 people, including some major dignitaries, out. And about a kilometer into its maiden voyage, a little bit of a breeze came up and it heeled over a bit and started taking on water through the lower gun ports. And it promptly sank to the bottom. 30 of the 200 people on board were killed. The rest were rescued. And this ship was obviously a rather poor design. So what does this have to do with our control? Well, I'd like to read to you a quote from the French philosopher Alain. So he said, "Every boat is copied from another boat. Let's reason as follows in the manner of Darwin. It is clear that a very badly made boat will end up at the bottom after one or two voyages and thus never be copied. One could then say with complete rigor that it is the sea herself who fashions the boats, choosing those which function and destroying the others. So who designs the boat? So let me put the question into a more modern form. Who designed Facebook? Naively, everyone says, well, it was obviously Mark Zuckerberg. But really? I mean, at the time Mark Zuckerberg developed the first prototypes of Facebook, there were thousands of competing systems with a variety of different designs. And some of them succeeded, rather few of them. Most of them died off. This is very typical of a Darwinian evolutionary process. And the Darwinian evolutionary process is not really so much designed as just it happens. So here's a more modern boat that is arguably, I mean, maybe there's more top-down intelligent design in this. There was a bunch of computer modeling to create the, to essentially replace a sail with a wing and so forth. But really, this is the result of centuries of experience with boats. And in fact, to borrow from Richard Dawkins, who claims that evolutionary processes are capable of much more complex and interconnected systems than any process of top-down intelligent design. And my claim is that we tend to think of technology development as top-down intelligent design. In fact, for most of my career, I've thought of most of what I've done. I've written a lot of software during my time. And I used to think that every program that I produced was the outcome of my deliberate, rational decision-making. And I now realize how much I was discounting the effect of the context in which I was working and the effect of how much the computers themselves were actually teaching me to write the program. Right now, today, when I work with modern software development processes, my decisions are forming a rather small part of the whole process. There's a very much of an evolutionary give and take here that's happening. And so top-down intelligent design is really not an appropriate way to think of how technology development is happening. So surely, I mean, everything I've presented is kind of negative. All these silver bullets, all of these things that people are trying to do to try to mitigate the risks of technology are problematic, to say the least. Well, there are opportunities, right? I mean, one of the things we could do, for example, if we have AIs involved in critical processes like finance, like processes that affect humans, like granting or denying loans, perhaps we need to license or certify them. I'm a proponent. I think that we do need to find ways to regulate technology, but I think we need, as technologists, we need to help the regulators, the people who design the laws, understand the limitations and the capabilities of the technology as best we can, because otherwise we're going to get regulations that are either ineffective or just that backfire. So licensing and certification might be one reasonable approach. We can also use AIs to expose human biases. We see this happening quite a bit now. The focus has been on, well, gee, the AIs are giving us biased decisions. But then if we look at why the AIs are giving us biased decisions, it's because there are biases in the data and the data is drawn from human activity. And so actually it's exposing human biases. We need to find some way to develop better recommender systems. And this is, I think, Stuart Russell's key point in his book, Human Compatible. He emphasizes over and over again that the optimization function that we're equipping these training algorithms with is really fraught, and it can lead to unexpected and very undesirable outcomes if you don't very carefully figure out what the consequences are of your optimization criteria. So I think that there's a good deal of research and opportunity there for figuring out how to do this better. The explanation machines that I described actually could prove useful to humans. So instead of, just being useful for satisfying some regulatory constraints, suppose that a judge could ask an AI to give it explanations for all possible decisions that the judge may be facing. This might actually help the judge break out of some preconceptions and come up with decisions that might in fact be better informed, because some of these explanations may actually lead to a change in the conclusion. We could use AIs to expose deliberate abuse of information filtering. One of my favorite examples of this is that ExxonMobil was recently caught presenting distinctly different ads to left-leaning and right-leaning viewers in Facebook. So to the left-leaning viewers, they were talking about their investment in renewals and the fact that they were reducing the carbon footprint of their operations. To the right-leaning viewers, they were talking about the fact that they were working towards reducing regulation and towards achieving energy independence. And this underscores the point that I tried to make earlier, that the problem isn't so much about the fake information, because none of this was fake. All of this was truth. Okay, these advertisements were about true things that ExxonMobil was really doing. But do we really want this kind of thing happening, where they are building on the biases that they can infer from the viewers, and then in fact reinforcing those biases? We can use AIs to expose this kind of abuse, and I think create an embarrassing situation for a corporation by putting this front and center. One key point is that these kinds of solutions all need a multidisciplinary engagement. These are not just technical problems. These are also societal problems, and we have to involve people who are sociologists, experts, legal experts, psychologists. It's very much a multidisciplinary problem. We need to break out of our little silos of intellectual activity, and this is really the major emphasis of this digital humanism effort. So just to suggest, if you would like to look into any more detail, here's a few sources. This Perspectives on Digital Humanism book might be a nice introduction. The two books that I published fairly recently on this topic are The Coevolution and Plato and the Nerd, and also specifically on the focus of the problem of deep neural networks. I actually, for the first time in my career, published a paper in a psychology journal that addresses this question about what deep neural networks can teach us about the psychology of decision making, in effect. So thank you very much. And with that, I'd like to open it up for questions.